All right, welcome to lesson 4-2. Today we're talking about limits and area. So there's that word again, limits. So you know that's going to be coming into play soon. So in the last couple of days, you've done a couple of different things. So in 4.1a, we talked about how we can approximate the area under the curve on some interval from a to b. And we can approximate that area using, say, rectangles or maybe trapezoids. For today, let's focus in on rectangles. Okay, so if I'm using, let's say, for example, these 5 rectangles here to approximate this area, remember one of the reasons why we know this approximation isn't going to be too precise is because sometimes, because it's a curve, sometimes the rectangle is going to be sitting below the curve, meaning we're going to be missing some area, and oftentimes the rectangle might actually sit a little bit above the curve, meaning we're going to have too much area that we're estimating. And so, of course, we know that our approximation is going to be a little too low or too high. So the question is, what can we do then to make this approximation a little bit more precise? Again, knowing it's still not exact, but what can we do to make it better? And so one thought is, well, of course we would want to minimize how much area we miss or how much extra area we have. And we might be able to do that by increasing the number of rectangles. So right here in this picture, I happen to be using 5 rectangles. Well, what if I doubled it? What if I cut each of these rectangles in half? And then, in this case, I was using a right-hand sum. If I were to redraw these by using twice as many rectangles. So then it would look something like this. Now notice all I did was I just basically split each of these rectangles in half, and then I redrew it, again, using the right endpoint. And as you can see, we already have a little bit better situation here. Notice that, yes, some of these rectangles still extend above the curve, but the amount of extra area that we have is significantly less than what we had when we were only using 5 rectangles. So again, by doubling the number of rectangles alone, we can already see that this approximation is already going to be a little bit closer to the actual area. Well, if having 10 rectangles was better, then what would be even better than that? Maybe 20, 50, 100? So how many rectangles would it take to make our approximation best? Well, the idea is we want to just make as many rectangles as we can. And in other words, we maybe want the number of rectangles to approach infinity. And there's that limit language that you hopefully were expecting. So again, the idea is we want the number of rectangles to increase without bound. Basically to the point where each of these rectangles is basically just a line, where it has almost no thickness or no width, has a little bit, and it's just the height. By having rectangles that are that skinny, we'd be able to basically completely cover the area under the curve with no extra at all. So that's the concept behind what we're doing now. So today we're no longer approximating area. Today we are actually going to be calculating area by utilizing the approximation idea that you did in 4.1a along with summations that you did in 4.1b, and combining those things together with limits so we can actually find the exact area. Okay, so to build up to that, though, we have a little bit of groundwork that we need to cover, just some details here. So let's start with that. So let's think about one of the rectangles that we're looking at here. So again, let's just go back to the 5 rectangles here for a second. So we're going to call the base of each rectangle delta x. And delta x, that's just the width of the rectangle, the base of the rectangle. And then remember that the height was going to be f of whatever this endpoint is. And I'm going to call that endpoint c sub I. c sub I. So if I is 1, then it would be c sub 1. If I is 2, it would be c sub 2. So in other words, it's the first endpoint, the second endpoint, the third endpoint, etc. Okay, so that means the area of one rectangle, is going to be base times height. So f of c sub I is the height times delta x, which is the base. But remember, to find the area, we're adding up all of these rectangles. And remember, if I'm adding up a sequence of numbers, that's the summation. So if I want to find the sum of n rectangles, then what I'm really talking about is the summation from I equals 1 up to n of those rectangle areas. So f of c sub I times delta x. So this right here actually represents the summation that we're doing to approximate the area, where n is the number of rectangles we're using. So for the second picture I drew, n would have been 10. For the first picture I drew, n could have been 5. Okay, so that's the idea here. So now, remember what I said though. If we want to make this no longer an approximation, but we want to make this the exact area, it means that we want the number of rectangles, n, to increase without bound. It means that we want the limit as n approaches infinity of that summation. And this is going to give us the actual area of that region under the curve. So let's work that into the official definition here for area. So let f be continuous, so remember no breaks, no asymptotes, no holes in the graph, things like that, and non-negative, so in other words above the x-axis. So let f be continuous and non-negative on some closed interval from a to b. The area of the region bounded by f of x, the x-axis, x equals a, and x equals b, so in other words, some region that might look something like this. Okay, so the area of that region is that limit as n approaches infinity of the summation from I equals 1 up to n of f of c sub I times delta x. And again, remember, f of c sub I, that right there is the height of the rectangle. And then delta x, remember that that's the base of the rectangle. Now down here it does define what delta x and c sub I are, and I do want to explain where those come from, but just so you remember, delta x is defined as b minus a, so it's the endpoints of the width of your interval, divided by n, and then c sub I is a, the start of your interval, plus delta x times I. So let me explain to you where those come from. So let's say that I were talking about some region from 1 to 3. And if I wanted to divide this into two equal width rectangles, how wide would each of those rectangles be? So hopefully you're saying they would each be 1, because you know that one of them would be here at 2, and then the other one would be here at 3. So if I had two rectangles from 1 to 3, the width of each of them would be 1. Well, what if I wanted 4 rectangles? Well, now how wide are they? Well, if I'm dividing them evenly, it would now be 1/2 of a width each. So if you notice, b minus a is measuring the total distance between them. So the total distance between 1 and 3 is 2. And then we're taking that width and we're just dividing it equally among however many rectangles we want. So if I wanted 8 rectangles, well, that would now be 3 minus 1, which is 2, divided by 8. If I wanted 16 rectangles, well, now it would be 3 minus 1 divided by 16. So if I want n rectangles, as this definition talks about, then that means I'm doing 3 minus 1 divided by n. So that's why delta x, which again is the base of each rectangle, is b minus a divided by n. So that's where that comes from. Now, c sub I, remember, that's referring to which endpoint we're referring to. Because remember, what that means is, for the first rectangle, so let's just say that maybe it's right here. This is c sub 1. Well, how would you get that value of c sub 1? Well, it's going to be a plus delta x. Well, the second one, again, assuming that these are equal width, this would now be c sub 2. How would I get that? Well, that's going to be a plus 2 delta x's, because it's a delta x plus another delta x. If I wanted to know c sub 3, well, c sub 3 is going to be, again, starting plus 3 delta x's. And so notice what's changing is how many delta x's we're counting. And remember, that's what the I, the index in a summation, does. It counts. So that's why if I want to know the ith c, the ith endpoint, it's going to just be your starting point A plus I delta x's. So however many delta x's you had to add to get to that endpoint. By the way, some of you might be wondering, why are we using a right-hand sum instead of maybe a left-hand or a midpoint? It's arbitrary, because remember, the idea is we want so many rectangles that they're not going to have much width to them at all. And eventually these rectangles are going to be so skinny, so narrow, that you pretty much can't see the difference between the left-hand sum, the right-hand sum, and the midpoint. Those rectangles are all going to be so narrow that there's pretty much no difference in their heights. Okay, so that's the idea. That's why we're arbitrarily choosing a right-hand sum for this definition. Okay, so that's where those two formulas come from. All right, so let's do an example here. So find the area of the region bounded by f of x equals x squared plus 1, x equals 1, x equals 4, and the x-axis. Sketch the region. Okay, so even though it says sketch the region last, let's actually sketch it first, just so we have a bit of a visual sense of what's happening here. So again, x squared plus 1, remember that that's just a parabola that's been shifted up 1. Ooh, that is messy. Okay, so parabola that's been shifted up 1. So again, just sketching. We're just sketching. And then x equals 1, so somewhere around here. X equals 4, somewhere around here. So x equals 1, remember, is a vertical line. X equals 4 is also a vertical line. Oops. And the x-axis. So remember, the region has to be enclosed by all of the boundaries they mentioned. So I have to be enclosed by this curve, by this line, by this line, and by the x-axis. So the region, hopefully, is jumping out at you as this region here. So that's the region whose area we're finding. And again, even though we are technically using these rectangles, this is no longer going to be an approximation. This is going to be the exact area. Okay, so in order to do that, we're going to use our definition, but to use that definition, remember there were certain things we needed to find. So the first thing I'm going to do is I'm going to find delta x. Again, that's the first thing, is I'm going to find delta x. Now, I'm going to sort of label it as steps. You don't need to do that in your work. You don't have to put step 1, step 2. I'm just doing this hopefully for organization purposes, so that hopefully you can follow the steps a little bit more clearly. As long as you are finding these things, that's the important part. So we're going to find delta x. Now that means first I need to know, what is my interval? What is my a to b? Well, if you look at the region, hopefully you recognize that when they said x equals 1 and x equals 4, that's actually your a and your b. So we're actually on the interval from 1 to 4. So that means for delta x will equal 4 minus 1 divided by n, and that's just going to reduce down to 3 over n. Okay, so that's the expression we're going to use for delta x. So the next thing we're going to do is now we need to find our expression for c sub I. And by the way, every year, some people, when they write this down, they think that because they look at their work, they think that that says C and then a semicolon, or that's a C, then because of the way they write it, it ends up looking like a G. So again, make sure you know this is C sub I. So C sub I, remember, that's A plus delta x times I. Well, our A is 1. Our delta x is 3 over n. So that means our c sub I expression is 1 plus 3 over n I. Or you can also write it as 1 plus 3i over n. You are welcome to write it that way, and depending on what you have to do with this expression, this might be a little bit simpler. It's up to you. It's a personal preference. Now, the next thing we're going to do, remember in the definition for the limit, it involves delta x, which we have, but it involved f of c sub I. So before we work with that expression for the summation, let's actually find our expression for f of c sub I. So we're going to actually do all of that work now. So find f of c sub I. Now again, f of x is x squared plus 1. So f of c sub I means that I'm going to replace my x with c sub I, which we just found is 1 plus 3 over n times I. And so now we need to expand this so that we can simplify it. And in the interest of time, I'm going to magically make that work appear. So this ends up becoming 2 plus 6 over ni plus 9 over n squared I squared. Probably the most common mistake is to forget that when you do 3 over ni times another 3 over ni, that gives you 9 over n squared. So just be very careful there. Okay, so the final step, but this is the part that's going to sort of involve the most work, is now we're going to just take the information we found and we're going to substitute it into the definition and evaluate. So remember, to find the area, it is the limit as n approaches infinity of the summation from I equals 1 up to n of f of c sub I times delta x. And so now we're going to substitute what we found for f of c sub I and delta x into this expression. So we now have the limit as n approaches infinity of the summation of I equals 1 up to n of, now f of c sub I, remember we had right there, that's 2 plus 6 over ni plus 9 over n squared I squared times delta x, which remember we found to be 3 over n. Okay, so now what's going to happen is, even though this ultimately is going to be a limit, we're going to have to spend the next several steps just working on this expression here. And this is what you were just doing in 4-1b. The idea is we want to rewrite this summation without the summation notation. So we want to write it purely in terms of n, using our summation rules and summation formulas. Okay, so again, just keep on writing that limit notation, just keep bringing it down, but we're not going to quite do anything with that yet. But for the rest of it, I'm going to move that 3 over n out in front, times, and then that's now going to be times the summation of 2 plus 6 over ni plus 9 over n squared I squared. And then now I'm going to go ahead and apply our summation rules, where I'm going to separate this into 3 individual summations and move the constants out in front of each of them. Okay, and when I do that, I end up with this expression right here. So again, notice I split it up into 3 summations, and then the 6 over n and the 9 over n squared, because those are constants, I move those in front. Now I can just apply our summation formulas to rewrite this. Okay, so that now becomes this expression here. So now, again, notice we have one term there, a second term here, and a third term here. And because at least one of those is a fractions, just like you did on previous assignment, we're going to go ahead and get a common denominator so that we can completely simplify the numerator. So that's what you're going to see me do on the next steps. Okay, so you'll see that I've done a couple of things here. So first, in that original expansion, I went ahead and simplified a little bit. So the 6 and the 2 were able to simplify. So the 6 dropped down to a 3, the 2 became a 1, and then these n's were able to divide out. Same thing in this third fraction here, that 9 and the 6 were able to reduce down to a 3 over 2, and one of the n's in this n squared canceled with the n up here. So that ended up becoming this step here. And then finally, to get my common denominator of 2n, I multiplied the first fraction by a 2n, so that's where I got the 4n squared. And the second fraction also gets multiplied by a 2n over 2n, and so the 3 times 2n gives me the 6n, and we still have to multiply that with the n plus 1. And then now all of my numerator can be combined. And so now I'm going to do a couple of things. So now I'm going to go ahead and expand the numerator so I have all the different terms and I can look for like terms. I'm also going to then eventually multiply the 3 over n, top to top, bottom to bottom. Okay, so I just did a bunch of work here. So notice again, I distributed the 6n, and I multiplied out the n plus 1 and the 2n plus 1, and that's where I got the 2n squared plus 3n plus 1. And then I was able to distribute the 3 into that. So finally, I had all my different terms, and then I combined my like terms, and I got 16n squared plus 15n plus 3 all over 2n. And then, finally, I was able to multiply the 3 times all of the numerator, and then the n times the denominator. So now, this limit is exactly what we did way back in Unit 1 when we were doing limits at infinity. And remember with that, the idea was we had a pre-calculus shortcut that you were able to refer to. Notice that the power in the numerator and the denominator match, so I already know that this is going to end up being the ratio of the leading coefficients. But remember, what I actually taught you in Unit 1 was to evaluate this limit, we factored out the highest power from the denominator, and we matched that in the numerator. So that those n squares cancel out, and then finally we get the limit as n approaches infinity of 48 plus 15 over n plus 9 over n squared all over 2. And then now, remember, as n approaches infinity, we can now evaluate each of these limits term by term. So the limit as n approaches infinity of a constant is still that constant, so 48, plus, remember, as n approaches infinity, 15 over n goes to 0. 9 over n squared also goes to 0. And then again, 2 stays a 2. I get 48 over 2, and that gives me 24. And what that means is the exact area of that region is 24. Now, I showed every single little step here along the way. I would not encourage you to take too many shortcuts because, as you can probably guess, there are far too many places for you to make a simple little mistake that taking shortcuts would make it too easy to overlook when you check your work. So again, you don't have to necessarily show every single little step that I showed on this work, but I certainly would encourage you to show most of this or much of this so that you avoid overlooking little mistakes that could happen, particularly, dropping a negative sign or, saying 3 times 3 is 6 instead of 9. So little things like that are what most likely would get you if you're not careful. Okay, so we're just going to do one more example, and because of the way that this particular function is and the endpoints of this interval, this one isn't going to be quite as much work, but I wanted to show you because it is entirely possible for us to do this even for a function that's in terms of y instead of in terms of x. And so it does initially require us to sort of flip our thinking a little bit. We need to look at things sort of slightly askew, but once you have everything set up, it then becomes exactly the same process. So again, find the area of the region bounded by f of y equals 2y plus 1, y equals 0, y equals 2, and the y-axis. Sketch the region. So just like the last time, we're actually going to start by sketching the region. Okay, now, f of y equals 2y plus 1. It's the same idea as if you were sketching f of x equals 2x plus 1. Now, if this were in terms of x, your y-intercept would be at y equals 1. Because this is in terms of y, everything gets reversed. So that means our x-intercept is going to be at positive 1. So I've got my x-intercept at positive 1. Now, if this were in terms of x, your slope would be 2 over 1, so you would go up 2 and right 1. But because this is flipped around, we're actually going to go right 2 and up 1. And then again, right 2 and up 1. So our function looks like that. So this is our f of y. And then remember, we're talking about y equals 0, so that's this horizontal line, which actually is the x-axis. Y equals 2, which is this horizontal line. And then the y-axis, so this vertical line. So the region that we're actually finding the area of is this region here. Okay, now, by the way, some of you might have noticed this region is actually just a trapezoid. So we could actually find this region very simply. We could actually just find it by finding the area of a trapezoid. However, we are going to do this one using the limit process just so that we can see another example using that limit process. But it would be a very easy thing to do to verify your answer by just finding the area of that trapezoid. Okay, so now remember, because everything is in terms of y instead of x, then that means we're no longer finding dx. No, we're finding, sorry, not dx, delta x. We're finding delta y. But we're finding delta y the same way. It's going to be your b minus a, so the endpoints of your interval. Now, normally your interval in terms of x are values of x. Because this is in terms of y, our interval has to be in terms of y values. So not side to side, but up and down. And so that means in this case, y equals 0, that's my a. Y equals 2, that's my b. So delta y is going to be 2 minus 0 over n, which is 2 over n. Now c sub I, we find that exactly the same way. It's going to be a, which is 0, plus delta x times I, which is 2 over n times I. So we're just going to simplify that to 2 over n I. And then that means that f of c sub I is going to be 2 times my c sub I, which is 2 over n I, plus 1. And that's going to just become 4 over n I plus 1. So that means our area is going to be the limit as n approaches infinity of the summation from I equals 1 to n of f of c sub I. So again, that's 4 over n I plus 1 times delta y, which is 2 over n. Now notice, once I put it in this summation, it doesn't even refer to the fact that this was in terms of y to start with. And the reason for that is this region could just as easily have been discussed in terms of x. I could form a region the exact same size and shape using a function in terms of x. So it doesn't really matter eventually that we were talking about this region in terms of y. We could transform that region to be the exact same size, but a different orientation, a different rotation. So that's why at this point, you'll notice it's no longer talking about a specific variable. Okay, so let's just finish this off. Okay, and so through the magic of pausing, here is all of the work. Go ahead and take a look closely at that. You can pause right now if you need to look more closely, but we do eventually end up with the limit as n approaches infinity of 6 plus 4 over n all over 1. And so when I evaluate that limit, so the limit of 6 is 6 plus the limit of 4 over n as n approaches infinity is 0, and then the limit of 1 as n approaches infinity is still 1, and finally we just get 6. Okay, so this is what it looks like to use limits along with our summation to find no longer an approximation for area, but the actual area of the region. All right, good luck. Again, my suggestion is work very, very carefully. Oh, and one last tip. If you get down here to the limit and you notice, say, at this step here, if you ever notice that the degree in the numerator, so the highest power on the top, is ever bigger than the denominator, you lost a power somewhere. Okay, so the degree of the numerator should never be more than the degree of the denominator. In fact, it should pretty much always match. You should always have the same degree eventually. So if you have it off, then you've made a mistake. Okay, good luck.